Okay, I'd like you all to take a look at this picture that I've got here, and it'd be interesting to know whether any of you know what this is a picture of. So what we have here is we've got a satellite, and this is a very famous satellite, and this is a satellite called the Hubble telescope. And as it suggests, it is a telescope which orbits around the Earth, and what it does is it's taking images or pictures of space, sort of planets, galaxies, etc. Now, the reason why this was sent up is because the quality of the images taken from outside of space, when you've gone through the atmosphere and you're outside of the atmosphere, the image quality is far better, far superior than if you were to take the images from Earth, because on Earth you would have elements of pollution, you would have the atmosphere that's affecting the light itself, so the quality is going to be different. Anyway, so one of the most famous images taken by Hubble, by the Hubble telescope, was an image where what they did was they looked at, if we looked at this image of space, we can see stars, we can possibly see some planets, and we can see galaxies. And what Hubble telescope then did was it took an image of the darkest parts of space. So it took an image of it. An image that it came up with, and what we've got to remember is when we look at this image, we can see billions of stars or millions of stars, and we can see many, many galaxies. But what was interesting about the image that it took was that it took an image of, I just want to open this link quickly. Okay, so here we can see it's sort of zooming in and it sort of focuses on a particular area within space. And when they looked at this area, the sort of closer they looked, it took a picture that looks like this. And this is a very, very famous picture because in this dark area that you see here, we can see many, many more galaxies in the far distance. And it's hard to imagine, each of these galaxies will have millions to billions of stars within each one. So it's quite amazing, this particular image they took. And when I saw it, the first time that I saw it, I was absolutely fascinated by this particular image that it took. Anyway, so our lesson today is going to look at the formation of the universe. Okay, formation of the universe. So our universe we have at the moment is filled with stars, galaxies, planets, solar systems, comets, and all those things. And what we're going to do today is we're going to look at something called the Big Bang Theory, which helps to explain where the universe comes from and everything that we find in it. And then we're going to look at the evidence we have that proves or that tries to support that we have something called the Big Bang Theory. Because the theory, it is what it is. It's a theory. It's an idea that we've come up with, but it's based upon evidence. And what we're going to do is we're going to look at this evidence. All right. So I know here I say there's two theories. There's a Big Bang Theory and something called steady state theory. I'm not going to spend too much time on the steady state theory, but I'm going to spend more time on the Big Bang Theory. All right. Now, if I just summarize it very briefly, what we have with the Big Bang Theory is that the universe began as a very hot, small, dense superforce. So what I mean by that is everything we have in the universe today, it starts off in a very, very small point. Okay, start off as a very small point, concentrated on this point. This point was smaller than an atom or atom sized, and this then very rapidly expanded into sort of the universe that we have today, sort of expanding. And the suggestion is that this event took place about 13.8 billion years ago. This started the Big Bang. It started the formation of atoms and everything else around us. So as a whole, we know that the universe, or we think that the universe is expanding, it's getting bigger, and the temperature is changing. The temperature is getting lower over time. So we're going to look at that in more detail. You don't need to write any of that down. Just be aware of sort of what we are looking at. So what we're going to do is we're going to break up the Big Bang into 7 phases. Okay, so there's different sort of phases or stages, sort of steps that's sort of happening at each step. So at the very beginning, we've got to understand, if we look at phase 1, is that right at the beginning, there was no universe, there was no space, and there was no time. So right at the beginning is when time started, is when this big occurrence happened. So this is time 0. So the universe started as a small point smaller than an atom. And in a fraction of a second, it expanded to something which is about the size of a melon, which is a large orange, into that size. And in this expansion, we will have, this would have taken 10 to the power minus 43 seconds. You can see that's sort of a fraction of a second. Okay, so in this expansion, we don't have any atoms. Okay, no solid particles or anything. It's just radiation, lots of radiation that's in this sort of, it's been formed at this point in time. Right, so phase 2. Now phase 2 is, and I've put this picture here, maybe I should not have included these, but what we've got to remember is when we talk about atoms, we talked about the electrons being on the outside of the atom, we talk about the nucleus, and inside the nucleus we find protons and neutrons, but what we haven't talked about is that protons and neutrons and electrons are actually made up of even smaller particles, okay? And you don't really need to know these names, but if you are going to remember one, quarks is one that you can remember, okay? So at phase 2, which is 10 to the power minus 32 seconds, we have the universe extremely hot. The temperature is about 10 to the power 27 degrees Celsius. Okay, so that is an enormous high temperature. Now this temperature, atoms can't form, and this is where we have the radiation and everything else. So no atoms, just lots of radiation, and this radiation would also include electrons and quarks flying around. So we just have electrons and quarks all flying around at this point in time. And what you've got to remember is we can't have any atoms because we don't have any protons and we don't have any neutrons. The electrons are around and these quarks are around as well. Okay. Now phase 3, we'll notice that this is now 10 to the power minus 6 seconds. So we're getting closer to a second, but not a second yet. Okay, and we find that the temperature is still very hot. It's 10 to the power 13, but you can see it's cooling down. It's cooling down right at the beginning. We're at 10 to the power 27. We're now down to 10 to the power 13. And unfortunately, this is at this point, what we have is that the quarks is now cold enough for the quarks to start clumping together. So they join together. And when they join together, they can start forming protons and neutrons. Okay. Now these protons and neutrons are just floating around. They have not combined into what we would call a nucleus at the moment. They're just sort of moving around. Okay. Now phase 4. Okay. Now this is the point where 3 minutes into the formation of the universe, 3 minutes, and the temperature is still very hot. It's about 10 to the power 8 degrees Celsius. So we still can't form any atoms. Okay, but here we have an opportunity for the protons and the neutrons to come together, so to form nuclei. So we start forming the nuclei, but not the atoms itself. It is now at phase 5 where we have the formation of atoms. You can see here we've got 2 atoms here. We've got hydrogen and we've got helium. And the reason why we've got hydrogen and helium is because these were the first atoms that were formed. And if you think very carefully about the work we did last term, is that hydrogen, or that an element is made up of a nucleus, and it's got particles inside the nucleus, and it's got particles on the outside of the nucleus, is that hydrogen is the simplest atom. So it's the easiest one to form. It will have one proton in the nucleus, one electron around the outside, and either 1, 2, or 3 neutrons in the middle. And helium, the same. Helium will have 2 protons, 2 electrons, and 2 neutrons. Okay, so these are the atoms that form first. So this is after 300,000 years. The temperature is a lot lower, much cooler. We've got about 10,000 degrees Celsius. And the electrons, protons, and neutrons can now combine to form small elements. Okay, so it's cold enough at phase 5 for these atoms to form. And we form hydrogen and helium first. And you can still see this is 300,000 years later, after the Big Bang. It's only at this point in time that we are forming atoms, or these elements. Okay. Oh, we can see my timing is very out here with the PowerPoint. Anyway, so phase 6, you can see here we've got a galaxy here. This is our Milky Way, and this is where we are. This is about 1 billion years, okay, and it's very cold now. We're getting to minus 200 degrees Celsius. And now we have, so we've got to remember, we've got hydrogen and helium, so floating around. And now gravity is making this hydrogen and helium coalesce, Okay, coalesce just means they move together. The gravity is pulling them all together, and they form these giant clouds of gas. Okay, giant clouds of gas, and this is an opportunity for it to form galaxies. So these dense clouds form galaxies. You know, galaxies is a collection of lots of gas particles, and also it gives opportunity where smaller gases are clumped together, form stars. Okay, this is self-formation of the stars, and this we're looking at 1 billion years after the start of the Big Bang. Now, phase 7 is probably a point in time where we are now, sort of a period where we are now. And you can see here, I've got a picture here, which is something we're going to look at in the next lesson, is the life cycle of a star. Life cycle of a star. So we have a star, and it goes through different phases. And at some point, what a star will do is it will die. And when it dies, it expels means sort of pushes out a lot of material into space. Okay, so we're looking at about 15 billion years after the Big Bang, okay, which is around about now. The temperature is extremely cold. It's minus 270 degrees Celsius, and there's something called absolute temperature. Okay, and that is a temperature where we can't make anything colder than that. And it's about minus 273 degrees Celsius. So looking at another minus 3 degrees Celsius to reach this temperature called absolute temperature. It's the coldest temperature that we can achieve. So this is close to that. So galaxies cluster together, stars start to die, and stars is where we find the formation of heavy elements like iron, lithium, and all those other elements that we are aware of now. It's at this point in time where these things form. And these elements that are sort of spewed out by a dying star now helps form planets and other stars. Okay. Alright, so what I'd like you to do now is there's a short video which I will sort of explain to you where that is, which I'd like you to watch, and then I would also like you to complete the worksheet that goes with the work that we did, so looking at the different phases. The focus here is on what happens at each stage, the time that it's taken to get to the stage, and also things like temperature changes that occur. Alright. Now, the next thing we need to look at is evidence of the Big Bang. Okay, evidence, things that we can say, well, the reason why we think there's a Big Bang, these are the reasons. Okay, now the first two reasons, and if you are ever asked, what evidence do we have of the Big Bang? First reason is of something called redshift. Okay, we are aware that there's something called redshift that occurs, and also because we are aware that this redshift shows us that our universe is actually expanding. The universe is actually becoming bigger. So if there was initially an expansion or a big explosion, which some scientists don't like us to use, it would start somewhere and then it will expand and get bigger. So we are aware that our universe is expanding. So I'm going to briefly explain what redshift is, and we're going to look at it a little bit later, trying to explain some more details. But when we look at a galaxy, now remember galaxies are made up of stars and so on. Stars give off light. Our sun is a star and it's giving off light. And what we can do is we can look at this light more carefully. And when we look or we analyze the light that come from different galaxies, we find that there are differences. We find that the light that we get from each one is different. Now, what we find is that galaxies that move away from us produce light that is redder. So when we look at the light, it's more red. This is something called redshift. And galaxies moving towards us is bluer. We have something called a blue shift. Okay? And what we find is that most of the galaxies are actually moving away from us. It's moving away from us. So again, it sort of gives us the indication that all these galaxies, it's part of the Big Bang, it's expanding and it's moving away. Okay. Now, if most galaxies are moving away from us, it means that the universe is expanding. Okay, so again, sort of evidence of our Big Bang. Now, if the universe is expanding, then in the past it must have been smaller. It must have been smaller. If we go back far enough to the beginning of the Big Bang, we can find that it would have originated from a particular point, which is the phase 1 we talked about. Remember, we say started at a point and then it expanded, and we can go back to this point. So what we see here is this is a galaxy. We can analyze the light coming from the galaxy, and we can look at it carefully, and we'll find that this wave pattern from a galaxy moving away from us is slightly longer, which means it produces more of a red color. So we call this a redshift. Light is more red, and this galaxy is moving away from us. Now, if we've got a galaxy that's moving towards us, okay, again, the wave pattern changes. The light coming from the wave pattern changes. And we find that we have more blue light. So this is called a blue shift. Light is more blue. And remember what we said is that most of the galaxies that we look at from Earth is actually moving away from us, which sort of suggests that everything is moving, it's sort of expanding. The universe is getting bigger. Now, what's quite interesting as well is if you look very carefully at the red, or you look at this wave pattern produced by the galaxy, the speed of this galaxy can also actually be determined by looking at, because the faster it goes, the more red it is, or the more blue it is, etc. So we can actually look at the speed as well. Now, the third one is something called cosmic microwave background. So again, if you ask, what's the evidence we have today that sort of proves Big Bang Theory, or the idea of the Big Bang Theory, you would say redshift, an expanding universe, and you would say cosmic microwave background radiation. Now what this is basically just saying that right at the beginning, when we talk about phase one, phase one is we had this expansion and we had no atoms or elements, we just had this radiation, lots of radiation. So phase two, lots of radiation, lots of heat. And if you look at the universe more carefully, we can see that there's this radiation emitting from space. When we look at this radiation, and we can't see this radiation because it's very, very cold. It's almost absolute temperature, almost minus 273 degrees Celsius. It's very difficult to see. So we use special instruments to see this radiation. We can actually see this radiation coming from space. And therefore it is sort of an evidence that this is what is happening. Okay, so as the universe expands, it stretches outward. It stretches this radiation outward. Now, steady state is just another idea. We're going to look at that briefly, not going to talk about it too much, but the idea is that the universe has always existed. It didn't start as a point and then expanded, it's always been there. Okay, the universe is expanding and constantly creating matter as the universe expands. So the idea is that the universe is expanding, and in this process it's actually creating new matter. And what that means is that the density of space stays the same. It doesn't change. It doesn't change. So at the moment, if you talk about Big Bang Theory, it would be very, very dense, high density, because it's, the entire universe is concentrated around a point. And then as it expands, the density of the universe is sort of decreasing because the volume is bigger and the mass is sort of spread out with this volume. But the steady state suggests that the density is always the same. The universe has always existed, and the new matter is just being formed constantly.